Time for us to do some problems involving trig substitution, which combines two beautiful ideas, trigonometry and substitution. And it helps us deal with a lot of problems. Mainly it helps us deal with square roots. So we're going to be seeing a lot of square roots today. And now we're going to be like, woohoo, we can deal with them. We have ways. And of course, it takes practice. It's important that we do practice. The more that we practice, the better we become. We want to become fantastic. We want to be the best. So make sure you do as much practice as you can. If you're following along with the video, make use of that pause button. If you see a problem, try it out yourself first. See how far you can get. Maybe you won't even need me. But if you did, I'm there. Just unpause me, and we can work it out together. Well, let's go have some fun, and let's begin. Our first problem. Find the square root of 1 minus x squared. Now, we've been kind of playing around with these problems when we have a definite integral. But indefinite, we've sort of steered away from for a while. And the problem is, there's challenges here. Well, but now we have a new tool, right? New tool, life is good. And in particular, we see, look, inside, what do we have? We have the square root of 1 squared minus x squared. We say, okay, all right. And in general, the principle is, if you see a squared minus x squared, well, that means the kind of substitution you should make is a sine, or you can make a cosine, doesn't really matter. Well, we generally use sine. So x equals a sine theta. So that's our substitution. In our case, a is 1. Okay, so here we go. We have the integral square root 1 minus x squared dx. And substitute. X equals sine theta. Dx, derivative of sine, is cosine. All right, good. By the way, the fact that the derivative of sine is positive cosine is why we generally prefer making the substitution for sine over the substitution for cosine. But either can be made. Okay, what else do we need to know? Well, we should know a couple of things. We should actually say, what is the square root of 1 minus x squared? Well, the answer is it's cosine. We're not going to worry about things like absolute value. Don't worry about that. All right, good. So, if you're wondering, where does that come from? Well, it's 1 minus sine squared is cosine squared. Square root of cosine squared is cosine. So what we have is the following. We're going to get a cosine theta from the square root of 1 minus x squared. All right, and then what do we have? The dx is a cosine theta d theta. So we have cosine times cosine, also known as cosine squared. Now, the next thing is, how do we integrate cosine squared? So we've transformed. See, we started way back, well, not that far back, square root of 1 minus x squared. It's like, okay, we no longer have a square root problem. Now we've turned it into a trig integral, and we say, well, now we have a trig problem. How do we go about integrating cosine squared? So for this, we say, all right, well, let's power reduction it, right? That's how we would do this if it was a trig integral, and it is a trig integral. So this would be 1/2, then it would be 1 plus cosine double the angle. So that would be 2 theta. Okay, good. Well, we can integrate that. So what does this become? So it's 1/2, integral of that is 1/2 theta. And then the integral of cosine is positive sine. There's already a half, but because of the 2 on the inside, we're going to bring another half down. So that'll be 1/4 sine 2 theta, and then of course plus c. Now, where do we want to go? We want to get back to in terms of x, because this is an indefinite integral. When you start with an indefinite integral, you need to have your answer is a function using the original variables. So we need to put everything in terms of x. we do know a couple of things. We know x equals sine of theta. And in particular, what that means is we can draw ourselves a triangle, because it really says, look, sine of theta is x over 1. So, drawing ourselves a triangle, put theta in the corner. Sine is the opposite over the hypotenuse, and we get the square root of 1 minus x squared is the missing side. That's the Pythagorean theorem. Not a coincidence, of course, that the square root of 1 minus x squared that shows up here matches sort of our motivation. It's not a coincidence at all. That's why we chose it that way. And we say, okay, well, great. What do? Well, we'd say, look, as long as we had things in terms of theta, life would be good. Unfortunately, that's a 2 theta. So that 2 on the inside is kind of messing us up. But the good news is we have ways to get rid of the 2. So double angle identities. So by applying double angle, what can we say? Well, we have the half theta still, and then sine of 2 theta is 2 sine theta cosine theta. Right? That's one of our identities. We'll just make a little note here so we don't forget. Sine of 2 theta, 2 sine theta cosine theta. All right. So when we replace sine of 2 theta, well, 4 times 2 is a half again. Sine theta cosine theta, and of course, plus c. And now we're ready to say, great, everything's in terms of theta. So we can say, well, what is theta? Well, if x equals sine theta, then we can also say theta is the arcsine, or the inverse sine of x. So we get 1/2 arcsine of x plus a half. Now, sine of theta, x, right? It's right there. Sine of theta equals x. Great. Cosine theta. Well, cosine is what? It's the adjacent over the hypotenuse. So that would be square root 1 minus x squared. So that's sine times cosine, and of course, plus c. And there we go. There we go. Done. Done. Wonderful. Beautiful problem. Beautiful problem. All right. Good. So let's do another problem. Okay, here we go. Next problem. Oh, it's a little shy. That's all right. Here we go. There we are. Find the integral, a similar problem, square root of 1 minus x squared, divide by x to the 4th dx. By making the substitution, x equals cosine theta. Now, there's a couple of things. First off, we're dividing by x to the 4th, but that's really not surprising. Here's something that people get uncomfortable with. They say, wait a second, I'm allowed to do a substitution with cosine? Really? And the answer is yes. You are absolutely allowed to do substitutions with cosine. And we'll get into that a little bit later, why you might want to. But the thing is, if you have an integral there where a substitution with sine would work, a substitution with cosine will also work. If you had an integral where a substitution with secant would work, a similar thing, you could substitute cosecant, it would also work. Tangent could be replaced with cotangent. Let's sort of work the problem through as it tells us. Then we'll sort of go back and say what was happening and what would we do in the future if we ran into something similar. So, well, we don't have any surprises. It's telling us what to do. So this is, woohoo, good stuff. So we have a couple of things. We know x is cosine theta. So that tells us that dx is negative sine theta d theta. That negative, it's my personal belief that because of that negative, that's why we discourage the substitution cosine. Just because so many people forget that minus sign. And we're trying to save you. We don't want you to make mistakes. We're We really, really don't want you to make mistakes. All right, good. Well, what else do we have? Well, we should talk about the square root. And the square root of 1 minus x squared becomes what? Well, it'll become square root of 1 minus cosine squared, square root of sine squared, makes it a sine theta. All right, great. Good. So, let's see what we get. Okay, so we have the integral square root 1 minus x squared divided by x to the fourth dx. Well, that would be equal to the integral. Square root of 1 minus x squared is sine. All right, so sine theta. Dx is negative sine theta. Then there's a d theta. And then x to the fourth is cosine theta to the fourth. All right, great. Well, now let's take a look, see what we have. Well, we can write this as integral minus sine squared over cosine to the fourth. Now, cosine to the fourth, because we see sine squared and cosine, whenever you see like sine over cosine, sometimes we like to say, maybe think of this in terms of secants and tangents. Because right now it's looking a little bit iffy, but let's think if we can do this in terms of secants and tangents. So the way to get tangents is to get sines over cosines. So I'll have a sine squared over cosine squared. Come up a little bit short on the cosines downstairs. So I'll have another 1 over cosine squared. All right, well, what's this? Sine squared over cosine squared would become minus tangent squared. 1 over cosine squared is secant squared. And now we're like, what? This is perfect. We know how to integrate this stuff. You see, what do we have? Well, it's the perfect combination where we have that secant squared on the end. We love it when we see a secant squared on the end because it's really well set up for a trig substitution. A nice substitution. We've already done the trig substitution. X equals tangent, right? Because then what happens? Not x. U equals tangent. Then what do we have? Du becomes secant squared theta d theta. And now, what do we have? Well, we'd have that this is equal to the integral, that tangent squared becomes u squared, don't forget the minus, secant squared theta d theta becomes du. Okay, so this is this nice integral, minus 1/3 u cubed plus c. It's kind of interesting, right? Because we started in something that was algebraic. This is algebraic. Square roots, powers. We transformed it to trigonometry by a substitution. Then we transformed again back to algebraic by a substitution. And we're like, wow, that one's easy. Great. So now we're not done. We got to step back. Go back to where we began. Okay, so say, all right, start with u. U is tangent theta. So this would be minus 1/3 tangent theta cubed. All right, plus c. So the last thing to do is to figure out, well, what is tangent theta? Now we can do it by drawing a triangle, or we could actually almost read it off, because we have sine and cosine. So tangent is sine over cosine, square root of 1 minus x squared over x. And we're done. But we'll go ahead and draw the triangle just for practice, right? It's good to practice. So we put theta in a corner. If cosine theta is x, well, we think of that as cosine theta is really x over 1. So the adjacent over hypotenuse, the opposite sign, square root of 1 minus x squared. And so we say, aha, tangent, opposite over adjacent, square root of 1 minus x squared over x. Yeah, we kind of said that before. So no surprises. So we have negative 1/3 times the square root 1 minus x squared over x cubed plus c. And we're done. Now, I'm going to pause before we jump to why did we choose cosine instead of sine. You might at this point be saying, could we have done other things? In other words, did we have to do a trig substitution? Now, on some problems, yes, and on some problems, no. Generally speaking, when you see it work out really well, and this is a case where it is working out fairly nicely, there could be other methods. The goal of trig substitution is just to say it's a relatively easier type of manipulation. Our goal in almost all integral techniques is how can we make things simpler? And sometimes some ways to make things simpler are easier. Sometimes some ways to make things simpler can be very messy. And so trig substitution is actually a relatively beautiful way to simplify things. So if you are doing some of these problems, and you're like, I'm not doing trig substitution, does that mean I'm doing it wrong? No, not necessarily. It is possible to do some of these problems without having to appeal to trig substitution. So just keep that in mind. Okay, now I said we would talk about why did we pick cosine, why didn't we pick sine? Because I think that there's sort of a nice lesson to be learned here. So let's suppose we had picked sine, x equals sine theta. Then what will happen is it'll feel really similar. So you end up with dx equals cosine. You end up with the square root 1 minus x squared equals cosine. And what does that do? Well, what it ends up doing is the integral becomes cosine, and the square root of 1 minus x squared is another cosine from the dx. So you end up with cosine squared over sine to the fourth. Now from here, why does this one not look as fun? Well, the same process would work, but we were dealing with cotangents and cosecants. And that's maybe a little bit less familiar. So that's why, in this case, it's a little bit better to do a cosine substitution, because we'll end up working with secants and tangents, versus a sine substitution where we end up working with cosecants and cotangents. But the thing is, other than keeping track of minus signs, the processes are the same for cosecant cotangent versus secant tangent. As a general rule of thumb, if you're ever doing a substitution and you get to a point in saying, oh man, these are terrible functions to work with, but if I could change the co-status, so in other words, I don't like working with cosecants and cotangents. Well, go back to where you started at the substitution and say, let me flip. So instead of sine, let me go to cosine. Then what happens is you flip the co-status, So in other words, if what was a cosecant now becomes secant, what was a cotangent now becomes tangent. And that's always going to happen. That's always going to happen. So just keep that in mind. It oftentimes doesn't make a difference, but from time to time, it's nice to be able to see what's going on. All right, good. Well, let's keep going. More problems. Oh, don't worry. We're not going to run out of problems anytime soon. So, our next one. Find the integral dt over the square root of 9 plus t squared. Okay, good. Now, we see a square root, so we're definitely like, oh yeah. Trig substitution. Good. And as we think of trig substitution, we think of what's the right form. Because there's, three possibilities. There's, if we see a squared minus u squared, okay, that tends to be something where we think of the a sine theta. When we see something squared, variable squared minus number squared, so I think of mu as a varying part. Well, that tends to be our secant theta. And of course, if we see variable squared and a number squared being added, doesn't matter which one goes first, that's a tangent theta. So here, 9, that's 3 squared. And then t is the part that's varying. So for us, we say, oh, since it's t squared plus 3 squared, that says our substitution that we should make is t, which is the varying part, is equal to 3 tangent theta. All right, wonderful. So what does that become? Well, it tells us that dt is equal to 3 tangent, almost made the wrong derivative. Derivative of tangent is secant squared. 3 secant squared theta d theta. Okay, good. And let's also talk about the square root of 9 plus t squared, because that's important to know. Well, that's the square root of 9 plus 9 tangent squared. Now, the nice thing is, of course, both terms have a 9, so we can pull that out. And the square root of 9 becomes 3. Square root of 1 plus tangent squared. Well, that's where we pull out our Pythagorean identities. 1 plus tangent squared is secant squared. And square root of secant squared is secant. And life is good. All right, so we know our substitution to make, and we've sort of identified what our pieces are. So let's see what we end up with. We have the following. We can say integral dt over the square root 9 plus t squared. All right, we can replace the top. That's going to become 3 secant squared theta d theta over, in the bottom, we're going to get 3 secant theta. Okay, well, this is working out rather nicely because we see the 3's are going to cancel. Cool. And actually, more than just the 3's, we can cancel a single secant. Say, fantastic. And really, this is just now the integral of secant theta. And that is on our list. In other words, it's one of the integrals that we know because there's 10 of them, right? There's 10 integrals that we should know by heart. And this is one of those. You say, look, that integral, that's the natural log of secant plus tangent. And of course, plus c. Now, we just have to know what's secant and what's tangent. But actually, we already know that because we can see them. See, tangent is right here. So tangent of theta is t over 3. So we can replace this by t over 3. And secant of theta, well, that's this piece right here. See, we see secant of theta, and we can say, that's going to be the square root of 9 plus t squared over 3. Now, if we didn't know that, what could we have done? One thing we could have done is we could come and make a triangle. Say, well, look, we know our original substitution, we write it as a ratio, t over 3. So, draw a triangle. Here's theta, opposite over adjacent, missing side by the Pythagorean theorem, square root of 9 plus t squared. So, secant would be adjacent over, hypotenuse over adjacent, and tangent opposite over adjacent. Now, let's write down what we have. We could write down, since they both have a common factor of 3 in the denominator, we might write our answer as square root of 9 plus t squared plus t over 3. And actually, that's a correct answer. But you might go and ask a calculator or some kind of computational software, and it might say the following. It'll say, hey, the answer to your problem is the natural log of the square root of 9 plus t squared plus t plus c. All right. Well, now I said it might, I don't know. It just depends. But I think it actually would say that. Now, if you look at these two, you might say, they're not the same. How could both be correct? Well, they're actually not quite the same unless you think about what's being represented. It does turn out they are equal if you understand what we mean by C. Remember, C is just a constant. And here, what you can do is, because you have a natural log of the square root of 9 plus t squared plus t over 3, well, when you have a division, natural log of a division becomes natural log of subtraction, top minus the bottom. So it can become the natural log of the top minus the natural log of 3 plus c. But then see, it says, wait a second, natural log of 3 is just a constant. I'm a constant too. Wah, 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 wah. And it absorbs that natural log of 3. That's why both of these are valid answers. The only difference between them is a term called natural log of 3, which is a constant, and that can get absorbed into the plus c. This looks a little bit cleaner, so that's probably why your computer, your calculator, whatever tool you're using, might be biased towards that one. But both are correct. All right, well, good. These aren't so bad. Why were we ever nervous about trig substitution? These are kind of fun. Well, of course, more to be done, right? Always more to be done. All right, well, let's try another one. Find the integral, -1 to 0, of dy over y squared plus 2y plus 2 quantity squared. Now, when you look at this, your probably first thought is, Steve, you've made a mistake. You've erred terribly. I was like, oh, what? What happened? What happened? What's wrong? There's no trig substitution for this. There's no square roots. Why are you thinking trig substitution? Okay, all right. I see where you're going with that. That's not a bad thought. So let's step back and think about what is the goal of trig substitution. We oftentimes say, oh, trig substitution, that's helping us get rid of square roots, because it really is a fantastic way to help us get rid of square roots. But more fundamentally, if you just dig a little bit deeper, the real goal of trig substitution is to help get rid of plus or minus signs in the middle of things. So if I have a square plus a square, or a square minus a square, I can use an appropriate trig substitution, and I can oftentimes say, get it down to a single term, which makes it easier to work with. So even though it may not look like trig substitution applies in settings like this, it can be. And I want to show you what to look for. I will tell you, roughly speaking, 95% plus, when you see the square roots, that's trig sub. And if there's not a square root, it's not trig sub. But just as a word of warning. Okay, it can be done and used in other settings. So, what happens here? Well, let's think of this quantity, y squared plus 2y plus 2 quantity squared. Now, if we are going to think trig sub, what we need to have are something like something that can change squared plus a number squared, or something that can change squared minus a number squared. But the key is we need to have squares. Y squared plus 2y plus 2 is not a square. But let's start with the y squared, and we'll add 2y. And now we pause and say, we really, really want a square. So what would I need to add to y squared plus 2y? Just this piece right here. What would I need to add so that the result was a square? Well, the answer is plus 1. So if we added 1 here, then y squared plus 2y plus 1 is y plus 1 squared, right? Yeah, it is. And then we say, well, but look, we have a plus 2, so there's really plus 1 left. So we have a y plus 1 squared. I don't think of it as a plus a 1 squared. That's the inside piece. So if we're putting on our trig substitution hat, which we're practicing trig substitution in our session, so we should be wearing that hat. We say, okay, all right, we have ourselves like a u squared plus a squared, which means our substitution that we should make is u equals a tangent theta. So in our case, our substitution would be y plus 1 equals tangent theta. Okay, so there we go. There's our substitution. All right, so where are we at? Let's clean up. We've been playing with our denominator. Let's see what this all becomes. So we have the following, -1 to 0, and we said by completing the square, we really have y plus 1 squared plus 1 squared squared. And now we're making the substitution, y plus 1 equals tangent theta, which, by the way, tells us that dy, taking the derivative, is secant squared theta, d theta. All right, so what do we have here? Well, this will become integral dy is secant squared theta, d theta. Downstairs, we're going to have tangent squared plus 1 squared. All right, and we'll clean that up in a second. Now, the bounds. Oh yeah, the bounds. Don't forget the bounds. So, because this is a definite integral. Now, whenever we're doing a definite integral, our philosophy should be always update the bounds, because we're on going forward. And the nice thing is, if we update the bounds as we go, we never have to go back. Always looking ahead, which is a wonderful thing about definite integrals. So let's take a moment here and think about our bounds. Let's start here with -1. And remember, when we write down -1 here, we're really writing down y equals -1. So y equals -1 to y equals 0. We want to convert to theta equals something to theta equals something. All right, so when we put in -1, -1 plus 1 is 0. What angle, when we plug into tangent, has an output of 0? The answer is 0. So our lower bound for theta is 0. All right, now plug in our upper bound of 0. 0 plus 1, that's 1. What angle, when we plug it into tangent, gives us 1? Well, that's actually a nice angle, pi fourths. So our upper bound is pi fourths. Great, good, progress. Now, let's keep making more progress. Tangent squared plus 1 is secant squared. So, what we really have downstairs is secant squared squared. Okay, that's a lot of secants. So, updating, we have the secant squared. Downstairs, secant squared squared is really secant to the fourth. And now we say, all right, well, we can definitely cancel a bunch of secants. And so we cancel. So this becomes 0 to pi fourths. And now we get 1 over secant squared. Well, how do we integrate 1 over secant squared? The answer is we don't. Not yet. We rewrite it. You see, what is 1 over secant? Now, oftentimes you say, well, look, there's this nice relationship. So if you were to flip secant over, you'd end up with cosine. So this is the same as 0 to pi fourths cosine squared. And now we're like, power reduction. Perfect. Something we feel pretty comfortable with. So this will become integral 0 to pi over 4, and cosine squared is 1/2 times 1 plus cosine 2 theta. And now we're in good shape. All right, we integrate. Well, the integral of 1 times 1/2, or if you like the integral of 1/2, is 1/2 theta. integral of cosine is sine. But because of the 2, we have to divide by 2. There's also a half there. So that would be plus 1/4 sine of 2 theta. Okay. Now, the nice thing is, because we've updated our bounds, we don't have to go back and say, well, let's figure out what things were in terms of y. No, no, no. Always move ahead. Always move ahead when it's a definite integral. So, now we plug in our bounds, and we see what we get. When we plug in pi over 4, a half times pi over 4 would give us pi over 8. 2 times pi over 4 would be pi over 2. And sine of pi over 2, well, it's a half, right? No, sorry, sine of pi over 2 is 1. It's 1. So it's 1 times a fourth. So pi over 8 plus 1/4. Good. Good. All right. And then what else? Well, plug in 0 and subtract. Well, if we plug in 0, we get 0 and 0. So that's gone. And so we're done. Done. Great. So it's pi over 8 plus a fourth. Beautiful. Beautiful problem. Beautiful answer too, isn't it? That's probably not the answer you would have thought when you first saw it, but of course you worked it through. And by making the right trig substitution, even though it may not be obvious, it came out very clean. All right, well, let's keep going. There's more beautiful problems yet to do. There's always more beautiful problems yet to do. A straight rod is 4 units long. So when we talk about straight rods, think of it as like a one-dimensional object. And it has varying density. So our density is 1 over x squared plus 9 to the 3/2. And x goes from 0 to 4. Determine the location of the center of mass of the rod. Okay, so this is fun. So we get to do a center of mass problem. It's a one-dimensional center of mass problem, so that's pretty good. And we have to think about, well, how do we do the center of mass? So we have to recall that, right? Now, the way I like to think about center of mass is it's sort of averaging location based on where the mass is at. So it's like, look, everybody gets to have a vote to where they think the center should be, but your vote is proportional to how much mass is where you're at. So places where there's a lot of mass, well, we should be biased to being near that location. In places where there's not a lot of mass, well, we shouldn't be biased towards that. All right, so what's the formula? Well, okay, so our center of mass, which we usually denote as x bar, it's a ratio. In the denominator, what you'll have is the total mass. So for us, since we're going from 0 to 4, we'll just put in 0 to 4, and I'll just write density. And we'll come back and work out that integral in a second. It'll be a fun integral. And then in the upstairs, we have, again, 0 to 4, because the idea is 0 to 4 is we're adding up. We have a density times a length. Density times length, that's the mass of a little piece, add up our pieces. In the upstairs part, we're going to take a moment. That's right, it's a moment. And what do we have? Well, a moment also has a location. So there's an x term. That's our location. And then we multiply that by the mass, which is the density dx. So that's the moment of a little piece. We add all our pieces together, and we get the moment. All right. So we're going to have to do 2 integrals. Good. Now, I suspect they're going to be very similar because the only difference is that x. Well, how big a difference can that x make? Well, we'll find out. Let's start with the denominator. Okay, what happens downstairs? So we would have the integral 0 to 4, and our density would be 1 over x squared plus 9 to the 3/2, right? Because I'm just copying down what the density is, dx. Now, what do we see? Well, we see, a squared, u squared plus a squared. So if we think u squared plus a squared would correspond to the substitution u equals a times tangent, well, for us, because it's x squared plus 3 squared, we say, ooh, that should correspond to the substitution 3 tangent theta. Whoops, sorry, x, not u, x. X equals 3 tangent theta. So that's our substitution to make. And the reason we're thinking trig substitution is we see square roots, right? Okay, well, dx would be 3 secant squared theta, d theta, that's good. And we should also talk about the square root of x squared plus 9. Well, what is that going to become? If we work it out, that would be what? Well, it would become 9 tangent squared plus 9 underneath. You can pull out the square root of 9, which is 3. Then you have a square root of tangent squared plus 1. Tangent squared plus 1 is secant squared. Square root of secant squared is secant. Okay, interesting. This is interesting things are happening here. All right, well, let's move forward. Okay, so, let's, I'm not going to worry about the bounds for a second here. Okay, so we're going to, the reason I say I don't want to worry about the bounds, I don't think they're going to be nice numbers. Certainly when you plug in 0, that's nice, but when you plug in 4, tangent theta equals 4/3. What? That's a little bit too messy for me. So I'm going to hold off on that. So let's just do the indefinite integral. Because that's always a choice. When you have an definite integral, you can always say, look, let me do the indefinite integral, and then I'll figure out the bounds at the end. So, okay, so the indefinite integral, 1 over x squared plus 9 to the 3/2 power dx. What would that become? Well, downstairs, this x squared plus 9 to the 3/2, well, that's the same as taking the square root of x squared plus 9 cubed. So that would become 3 secant theta cubed. On the other hand, what is dx? Well, dx is 3 secant squared theta, d theta. And we say, okay, well, things are looking promising. Let's talk about our 3's. We have 1 3 upstairs. We have 3 3's downstairs because it's 3 cubed. So if we cancel off a single 3, we're going to be left with 1/9. So that's our constant. Now let's talk about our secants. There's 2 secants upstairs, secant squared. There's 3 of them downstairs, secant cubed. So if we cancel the secants, that's 1 over secant. Oh, okay, well, that's not so bad. That would be what? Cosine. Oh, lovely. And then cosine, integral of cosine, is sine. Perfect. Now we have to say, okay, well, what is sine? Okay, well, for that, we have to draw our triangle. So, come in. We have space. We'll put our triangle in here. So, put theta in the corner. And we say, well, what is it? If we solve for tangent of theta is x divided by 3. So, it's a ratio. Opposite over adjacent. So x over 3, which means that our missing side, the hypotenuse, would be square root of x squared plus 9. All right, there we go. So what is sine? Well, sine of theta will be what? It's going to be equal to the opposite over the hypotenuse. So we end up with 1/9 times our x over the square root of x squared plus 9. All right, great, wonderful. Now, we're ready to talk about our definite integral. Because how do we finish? Well, we do the bounds now. Okay, so let's move this up, give ourselves some space. So our integral from 0 to 4 of 1 over x squared plus 9 to the 3/2 dx is, well, 1/9 times x over the square root of x squared plus 9. Evaluate from 0 to 4. The nice thing is when we plug in 0, we get 0. Woo! Nice! It's wonderful that we're getting 0. What happens when we plug in 4? Well, we're going to get 4 on the top. Okay, that's beautiful. 4 divide by, downstairs we have a 9, and then we have the square root of 4 squared plus 9. Well, 4 squared is 16. 16 plus 9 is 25. So it's 4 over 9 times 5. Or if you like, 4 over 45. All right, so that is the denominator. We're halfway done. And at this point, you're like, oh my gosh, we've got to do that all again. Well, we've got to do something. Okay, so let's update. So this is 4 over 45. There we go. All right. Well, what do we need to have happen now? For the next thing, we need to now say, okay, the numerator. Well, the only difference is we're adding an x. So what do we do? Now, let's write down that integral. So we have the integral 0 to 4 of x times 1 over x squared plus 9 to the 3/2 dx. Now, we can actually do trig substitution again. We absolutely can. What would happen? Well, the only thing that would happen is essentially we'd have an extra piece here, which would be, because x is 3 tangent theta, we'd have like a 3 tangent theta here. And so we'd have like a tangent theta over a secant theta. And we'd, proceed, dot, 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 dot. And it would actually work out fairly similar. But do we have to do that? And the answer is no. Look, just because trig substitution can work doesn't mean that normal substitution can't work. Sometimes normal substitution works perfectly fine. So let's take a look at what we have here. Is there a nice substitution to make? I claim the answer is yes. There's a lovely substitution to make. Namely, let u equal the inside. Because what happens if you let u equal x squared plus 9, our du, well, that's 2x dx. I have an x dx. All right, look, now I have a 2x dx. Aha! And you're like, oh, Steve, you can't do that. You just wrote a 2 there without doing anything. You're right, I didn't do enough. I'll put a half. See, a half times 2, things cancel, back to where we began. Okay, but now, see, look, it's perfect. It's perfect. Why? Well, this becomes integral. I still have the half. 2x dx is du. 1 over x squared plus 9 to the 3/2. Well, that's 1 over u to the 3/2, which we'd write as u to the minus 3/2. Now, don't forget the bounds. Plug in 0. 0 squared plus 9. 9. Plug in 4. 4 squared plus 9. 25. Now, let's integrate. So, 1/2. If we add 1 to the exponent, we'll get negative 1/2. And then we have to divide by negative 1/2, which is the same as multiplying by minus 2. and evaluate that from 9 to 25. Okay, well, the 2 and the half, they cancel. And so what we really have is minus 1 over square root of 25, which is 5, minus minus plus 1 over square root of 9, which is 3. So it becomes minus a fifth plus a third. Common denominator is 15. So this is minus 3 over 15 plus 5 over 15, which is 2 over 15. All right, that worked out pretty well. And here, just normal substitution. So don't get sort of like blinders on where it's like, if I see a square root, I can't do anything other than a trig substitution. That's a bad mindset to be in. Put yourself in a happy mindset. Be like, hey, what are some possibilities? Be open that there might be more than one idea that could work. So let's write that in here. So 2/15. And now we'll clean it up. Okay, so this is the same as 2 over 15. Bring the denominator up by doing a reciprocal. 45 over 4. Say, ooh, well, this is nice, because look at the 15. 15 goes into 45. Okay, that's good. That makes that a 3. And 2 goes into 4. That makes that a 2. And so we end up with an answer of 3 over 2. All right, nice. Now, we should sort of pause and ask, is it reasonable? I mean, hopefully it's more than reasonable. Really, we hope it's correct. But okay, how could we say, is it reasonable? What's sort of our criteria for reasonable? Well, we know we're only going from 0 to 4, so it better not exit from 0 to 4. Well, the good news, 3/2, it's between 0 and 4, so that's good. The other thing we might say, okay, well, it seems to be biased closer to the 0 side than it is to the 4 side. Does that make sense? So in other words, is there more density near 0 or near 4? Because we should be headed to whichever side has more density. And we see as x increases, the density goes down because, as x increases, the denominator gets larger, whole expression gets smaller. So it says, ooh, I'm denser near 0 than I am at 4, so I should be a little bit biased towards 0. And that's what's happening with 3/2, right? Because the middle would be 2, so we're biased closer to 0 than we are to 4. So this is good. It's a sign that we probably did things right. Isn't that a great sign? We love it when we do things right. It just makes it feel like we're learning. That's a wonderful feeling. All right, good. Well, fun problem. Nice application. All right, let's keep going. More problems. So, our next one. Find the integral 1 divided by y cubed square root y squared minus 1 dy. Okay, good. Again, not an obvious substitution. It looks like a trig sub because we see a square root and there's not something else calling out to us saying, hey, here's a simple thing to do. So let's work on the trig sub. Well, when we look at it, this is of the form variable squared minus constant squared. And when we see that, the substitution to make is secant. So in our case, because it's y squared minus 1 squared, we say, okay, we're going to make the substitution y equals secant. All right, that seems reasonable. Well, maybe. Let's find out what happens. I don't know. Well, we do need to do a couple of things. What is dy? Well, derivative of secant theta, tangent theta, d theta. Okay, how about the square root y squared minus 1? Well, secant squared minus 1 is tangent squared. So the square root of y squared minus 1 is tangent. That's why we make our trig substitution, because we can actually replace the square root by something nice. All right, so making our substitution, we get, well, 1 over y cubed, secant cubed. All right, the square root of y squared minus 1, tangent. The dy is secant theta, tangent theta, d theta. Okay, wow, this one has a familiar ring to it. You're probably thinking, my goodness, all these problems are kind of familiar. Well, they all come into trig integrals, and there's only so many techniques you can use. So don't get too caught up in like, oh, we're going to always keep seeing the same thing. We'll see some other things too. Don't worry. Well, what are we seeing? Okay, we can do a couple of things. We can cancel off a tangent. We can cancel off one secant. So we really have a secant squared downstairs. But we say, whoa, flip that over, secant squared. That becomes cosine squared. So now we say, look, this is the same as integrating cosine squared. All right, well, we know how to integrate cosine squared. We've done it before. In fact, we've done it very recently. Power reduction. Cosine squared is a half times 1 plus cosine 2 theta. Well, so that integrates. There's a half theta. Then the integral of cosine is sine. You have to divide by 2 because of that 2. There's a half out there. So that's 1/4 sine 2 theta. All right, and plus c. Now, we need to get back to just theta being our function. So, sine of 2 theta, it's a wonderful function, but not for our purposes. In order for us to figure out how do we get back in terms of y, because we started with y, how do we write that in terms of just sine of theta or cosine theta or something, and double angle. So that's 1/2 theta, and sine of 2 theta is 2 sine theta cosine theta. So that's 1/2 sine times cosine plus c. Now, we can come back here. So we're told, or maybe that's not the right way to say it, we chose wisely, because we were able to integrate, y as secant. Well, that's really secant over 1. So, when we draw our triangle, we have theta in the corner. Now, secant is what? It's the hypotenuse over the adjacent. It's the reciprocal of cosine. So, hypotenuse over adjacent, which means that the missing side, no surprise, is the square root of y squared minus 1. So, what does that tell us? Well, it tells us that our sine, which is the opposite over the hypotenuse, that would be the square root of y squared minus 1 over y, and the cosine, which is the adjacent over the hypotenuse. So that's 1 over y plus c. And, whoops, we forgot theta. Well, how do we do theta? Well, secant of theta equals y, so that tells us that theta is arc secant. Now, some calculators really don't like arc secant, and so if you plug it in, it won't give you an answer in arc secant. So you'll see kind of weird functions. One thing it'll say, oh, it's really arctangent of the square root of y squared minus 1. And you go like, okay, where's that coming from? And it comes from the triangle, right? Tangent of theta is square root of y squared minus 1. So you could also say theta equals arctangent of square root of y squared minus 1. But I think this is just so pretty. So our final answer, 1/2 arcsecant of y plus 1/2 square root y squared minus 1 over y squared plus c. And there we go. And like I said, arcsecant, there's a couple ways to write that. So depending upon what program or calculator you're using to double check your work, and it's not a bad idea to double check your work, they might write it in several different ways. Okay, cool. Now it's kind of interesting if you compare it to some of the earlier problems we did, we actually saw things like integral of cosine squared, but we got really different looking answers. And you might say, whoa, why are our answers looking so different? Well, the answers look really different because of the kinds of substitutions that we made. In those cases, we made other types of substitutions, and therefore, when we unraveled our answers, it would look very different as we came back. So, it's not such a bad idea to see something showing up multiple times and saying, ooh, there's some interesting variation. Wonderful, beautiful stuff. Great. Well, another problem, right? Of course. We should always keep working. The more we do, the better we get. So, our next problem. Find the integral, the square root, t squared plus 2t dt over t plus 1. Oh, okay. This one looks like something. It's not so clear, right? I don't think this one, it's not so obvious where to start. But let's not panic. I think it's nice to look at a problem and start to ask ourselves the question, what could we try? Well, you might think of substitution, like, okay, t squared plus 2t, if you did that, you get a t plus 1, which is great, except it's in the wrong place. It's down there. See, if it was t plus 1 upstairs, life would be good. So I don't think a normal substitution is the right way to approach it. Now, of course, we're doing our trig substitution practice, so we should put on our trig substitution hat. Say, okay, if we were doing trig substitution, what would we do? Well, there's a square root, so what we should do is think about, we want to write things inside the square root as something which is varying squared and some other terms squared. So let's think about what we have inside. We have a t squared plus 2t. Now, that's not a square. I really want to make it a square. Right now it feels a little bit incomplete. So is there something we can do to complete the square? That's right, we can complete the square. Of course we can, right? So here, if we were to add one more, then we'd be like, woohoo! This makes it t plus 1 squared. Great. But of course, I can't just add 1, so we'll also subtract 1. So subtract 1 squared. Now, we sort of say, oh, this is promising. And the reason we say, this is promising, is notice that the t plus 1 there matches with the t plus 1 downstairs. So that's actually a good sign. I feel like we're going in the right direction now. Well, okay, so now what do we do? All right, well, we see we have a t plus 1 squared minus 1 squared. So that's a variable squared minus constant squared. So in particular, we know when you have u squared minus a squared, our right substitution to make, that's our secant substitution. So for us, we say, okay, the part that's varying, that's our t plus 1 equals secant theta. So that's our substitution we're going to make. T plus 1 equals secant. Now we should go through and figure out what are some things which go along with this. For instance, if t plus 1 equals secant theta, then we can say dt, well, that's going to be secant theta tangent theta plus, dt. Secant derivative not ingrained. Aha. And it's not dt, Steve. It's d theta. Okay. All right. Good. Well, we'll get there, right? We'll get there. It's all right. It's easy to make small mistakes, but we correct ourselves. Small mistakes, Well, small corrections. And the sooner you correct, the better. That's why it's always good to okay, I just did a computation. Does it look right? Oh, wait, something feels off with the notation. Oh, yeah, there was a small mistake. Fix the notation. It's like flying planes. The way they used to fly planes is that there'd be big correction, do. But now you fly a plane and it's amazing. It sticks super, super close. Why? Well, the computer is making thousands and thousands of corrections all the time. And whereas pilots, it would drift way off course and got to make a big adjustment, and then big adjustment. And whenever you make a series of big adjustments, it's kind of wasteful. But if you can just make a series of very small corrections, it's much more streamlined and more efficient. So that's why check your work as you go. Don't be like, okay, let me wait till I'm halfway done and then I'll look at the work I've done. No. That can really cost you. Okay, so what do we have? Well, we have the following. Let's see. Downstairs, that's nice. Secant. Good. Now, here, square root of secant squared minus 1. Now, we know why we made the choice of secant. Secant squared minus 1 is tangent squared, so it becomes the square root of tangent squared, which is tangent. So that tangent here comes from reducing. Okay, now we haven't done the dt yet. So that's secant theta, tangent theta, d theta. And, we get a little cancellation. We love it when we get some cancellation. It makes us feel like we're making progress. And we say, okay, great. Actually, this is pretty good. Because what we've now gone to is the integral of tangent squared. Now, how do we integrate tangent squared? Well, we do it by rewriting it. And we use our Pythagorean identity. Remember that tangent squared plus 1 equals secant squared, or tangent squared equals secant squared minus 1. We actually mentioned that up here, right? Okay, so this is the integral of secant squared minus 1 d theta. Well, now we're in great shape. Integral of secant squared is tangent. Good. Integral of 1 is theta. And of course it's an indefinite integral, so plus c. So we're almost done. The last part is we have to say, look, we've got to go back. What is it in terms of our original variable? Okay, so let's see what we have. We have that secant of theta is t plus 1, which we think of as t plus 1 over 1. So we can come in, draw a triangle. We can put theta in the corner. So here's theta. Now, secant is hypotenuse over adjacent. T plus 1, 1. And this last side, well, it would be t plus 1 squared, subtract 1 squared, square rooted. And so you can write it that way, t plus 1 squared minus 1 squared. But it simplifies to, can you guess? Oh, don't have to guess. It's t squared plus 2t. The original term, the thing that got us going down our path here. All right, well, so we're pretty much done, right? We just need to find, well, what's tangent? Tangent is opposite over adjacent. So that would be the square root of t squared plus 2t minus theta. Well, take arcsecant. So arcsecant of t plus 1. And then plus c. And we're done. Nice! What a fun problem. Good stuff. Good fun problem. Okay. Well, I think we probably have time for one more. One more. All right. So, find the integral of cosine of z over the square root 3 plus cosine squared of z dz. And this one will probably make us say, huh, it's already trig, isn't it? How do we do a trig substitution when it's already trig to begin with? Well, let's think about it. Now, one of the things that we spot is like, ooh, I see a cosine z dz. So mentally in our mind, we would say, you know, this is the same as writing the following. 1 over the square root of 3 plus cosine squared z. And then put that cosine z on the end. So cosine z dz. Now you might say, why would we mentally do that? Well, kind of what I like to look for is we want to say you should look for substitutions, right? And so when you're looking for substitutions, you're looking for something that should become a du. And so in particular, you look for things that are common derivatives. You say, cosine z is the derivative of something, and it's just sitting right there. So it could be, this might possibly act as a good choice for du. I'm not saying it is. I'm not committing yet. But if I were to do that, then what I would want to do, in order to pull that off, I would say, well, that would say that everything else has to be in terms of what would lead to the derivative being cosine, which would mean I need everything else to be in terms of sine. Okay, so I want to ask the question, can we rewrite using sine? And if we can, that's a good thing to do, because then we're like, okay, so we can make some nice substitution. Now the good news is the only thing right now is that cosine squared, and then we're like, oh, yeah. There's a nice connection between cosine squared and sine. In fact, it's one of our favorite identities, the Pythagorean identity. Cosine squared is 1 minus sine squared. Okay. So what do we have? We can write this as 1 over, I'm going to replace cosine squared by 1 minus sine squared. And we can say square root of 4 minus sine squared. And a cosine z dz. Now, notice what we have inside our square root. Well, it's something in the form a squared minus u squared. And when we see that, our rule is to say, here's something you can try. Let u equal a sine theta. So in our case, well, it's 2 squared minus sine squared. So this is suggesting that try the following substitution. We're going to let sine of z, this inside part, be equal to 2 sine of theta. Okay, well, let's just try it. You know, the only thing we have to lose is maybe a little bit of work, but that's okay. It doesn't hurt if it succeeds. Wow, that'll be cool. Okay, well, so taking derivatives, what do we get? Well, derivative of sine, cosine z dz. Perfect. Perfect. Mwah! I already feel like this is a beautiful substitution to be making. Is equal to, here, 2 cosine theta d theta. All right. Well, that's promising. Now, what else? Well, we can say, look, the square root of 4 minus sine squared becomes what? Well, it's the square root of 4 minus 4 sine squared. But instead of z, theta. We can pull out the square root of 4. that would be 2. And 1 minus sine squared becomes cosine squared. When you take the square root, you're left with cosine. So, what do we have? Well, downstairs becomes 2 cosine theta. Right? The square root of 4 minus sine squared z becomes 2 cosine theta. Upstairs, the cosine z dz is 2 cosine theta d theta. That's looking pretty good. As integrals go, you really can't do a lot better, right? Because the 2's cancel, the cosine thetas cancel, which means that what we have left is the integral of d theta. Favorite integral we could have. Theta plus a constant c. So the only thing left to do is say, well, what's theta? Okay, for that, we come back to our formula. Well, our formula says sine of theta times 2 is sine of z. So sine of theta is 1/2 sine of z. So to get rid of the sine, we can say theta is arc sine of 1/2 times sine z. And there we go. In fact, that's our answer, right? So just what that part is, arc sine of 1/2 sine z plus c. Wow. Now you might say, ooh, aren't arc sine and sine inverse functions of each other? So doesn't that become like a half? No. Unfortunately, that extra half there in between kind of throws a wrench into the things. And so it doesn't simplify quite so nicely. But still, all in all, what an answer. Kind of fun. And probably not what we would have thought when we started. But by making a trig substitution, even though there was already trig there, it worked out. And we got what we needed. Well, I don't think we can top that one. So it's good that we're stopping here. Keep practicing. The trig substitution is one of those things that once you get the hang of it, it's actually not bad. It just says, oh, let me make a good substitution, and then we convert, and now we're just doing more trig integrals. And who doesn't love a good trig identity? So keep practicing, and pretty soon you'll start to enjoy them more and more. It'll become something that, my goodness, could be fun. Yeah, it could be. All right. Take care, and hope to see you again soon.